Welcome to Ask and Learn.
Okay guys, today we're answering a question from chapter 20, section 8. Let's get started. The question says we have 2 moles of an ideal gas that occupy a volume V. So let's go ahead and write N, our number of moles, is equal to 2, and our initial volume V1 is equal to V. The gas expands isothermally and reversibly to a volume 3V. This means that our final volume, which we'll call V2, is equal to 3V. And because it's isothermal, we'll make a note that says delta T is equal to 0. Part A asks us, is the velocity distribution from the isothermal expansion changed? So recall from equation 18.16, we have that the average kinetic energy of a gas molecule, which is given by 1/2 mv squared, where m is the mass of the molecule and v is the average velocity, is equal to 3/2 kT, where k is the Boltzmann constant and T is the temperature of the gas. Because we said earlier that in an isothermal expansion, delta T is equal to 0, what this means is that the right-hand side is then a constant. So the left-hand side then must also be a constant, which means that velocity can't change. So we know that for part A, the answer is no. Let's move on to part B. Part B asks us use equation 20.23 to calculate the change in entropy of the gas. Equation 20.23 is written delta S is equal to K ln omega 2 over omega 1, where omega 2 and omega 1 represent the number of accessible states to the gas in states 2 and 1, respectively. So let's take a closer look. If we know that initially we have omega 1 accessible states in a volume V, and we expand to a volume 3 times that of our initial volume, what this means that each molecule now has 3 times as many accessible states. But because we have n total molecules, this means that omega 2 is equal to 3n omega 1. So let's plug this back into our equation, and we'll get delta S is equal to K ln 3n, which is equal to n k ln of 3. Now we don't know the total number of molecules yet, but we do know that we have lowercase n equals 2 number of moles. So we can rewrite this expression as lowercase n times Avogadro's number n sub a times k ln of 3. If you plug all of these values in, you will find that delta S is equal to 18.26 joules per Kelvin. Now let's move on to part C. Part C asks us use equation 20.18 to calculate the change in entropy of the gas. Compare the result to that obtained in part B. So equation 20.18 tells us that delta S is equal to Q over T. But we don't yet know what this Q is. Let's take a look at the first law of thermodynamics, which tells us that du, the change in internal energy of the gas, is equal to dq, the heat put in, minus dw, the work done by the gas. So again, this du term is referring to this 1/2 mv squared, the internal energy of the gas, which we've said does not change in an isothermal expansion because delta T is 0. So this first term goes to 0. What this means then is that dq is equal to dw, the change in work. But we know that for a gas, work is equal to P delta V. So we can rewrite this expression as P dV. Now I'm going to write the ideal gas law on the right-hand side because I'm going to use it to replace this term P in our equation. So we have PV is equal to NKT. This is one form of the ideal gas law. And there's also another one, nRT. These are equivalent. Because I had used capital N and the Boltzmann constant in part B, I'm going to go ahead and use this form of the ideal gas equation, but keep in mind that both are equivalent and you're free to use this one as long as you convert back from R to K. So if we plug this in, we get dQ is equal to NKT over V dV. Now we can integrate both sides and we'll find that Q is equal to NKT ln of V. But remember that we're integrating from V1 to V2. So this is actually going to be V2 over V1. And this is equivalent to NKT ln of 3. So going back to our original equation, delta S equals Q over T, we can plug things in and find that here delta S is equal to NKT over T ln of 3. The T's cancel out. And now if you'll notice, we have NK ln of 3, which is exactly the same expression as we had in part B. So this also gives us a value for the change in entropy of 18.26 joules per Kelvin. Thanks, guys. I hope this helped.